In this testing video, I'm going to show you how my computer runs a sample piece of code. This program is simple, but demonstrates the function of the ALU and a branch instruction. The first line performs a logic AND between registers 11 and 12. It saves result in register 9. The observant will see that the homebrew computer has only two registers, op2 and op1. The reason why this works is because the programming environment manages virtual registers in RAM, 12 of them in fact. If the if could be thought as pointless in this program, however, it shows the ability to branch, and that's all it needs to do. It branches to a different instruction within RAM, even if the latter line doesn't get run. Anyway, we've switched over to the programming environment. This programming of the first line and the branch instruction and my instruction to do if false should follow after this. Now the reason why I write this is because if I change the condition at a later stage and it turned out to be false, and it wasn't branch always instruction, it was conditional branch instruction, the program would run faster, would run this latter line, not faster. Next, the label identifier to branch to should be written, and then the instruction to do if true. So it's always going to be true, so this is the one that's going to be written, not written, run. This program will always branch to this label, but this is because the condition in the imperative language says always true, so it's a battle instruction, a branch always instruction. However, this program has a logical error in it somewhere. If the condition was changed to false, the program would execute both instructions because it would branch to. So what we'd have to do is have a label there and a label at the bottom, and this would stop the latter and instruction from executing. Okay. This code should work. Okay. The top line will load a value from the virtual register 11 into ACK. It has the correct mnemonic, and the opcode points to that register 11. The next line has the correct mnemonic, and it will move the value of the accumulator into register 1, op1 even, and the reason why it's all zeros is because op1 register address will have all zeros. It's only the last bit really that addresses the registers, because there's only two registers in the system, op1 and op2. The next instruction will move the NAND result into the accumulator. Next instruction after that will store the accumulator value into the last value in RAM, where all the local variables are kept for the libraries. Local variables are used in the last bit of RAM, because so they don't interfere with the first bit, with the instructions at the start of RAM, and then that data that got saved in the last address is loaded back into the accumulator and then moved into op1, and the same happens again. The same data gets moved into op2, and the resulting NAND gets put into the accumulator, and gets stored in the virtual register 9. Now what this does is it's done 2 NAND operations. It's got 2 operands and NANDed them, and then got the result and put it onto both inputs of the second NAND, which effectively makes an AND, and that's the instruction that we've got. The branch instruction goes to line 27. Yeah, it's a bit further up, line 27 there, and that just branches past all of this, which is, yeah, branches. And this code is exactly the same as the one that we've just done, apart from it sets it to a different register, I think. Then this is the second branch instruction, goes to line 39, which is the end of the program. So yeah, that's the code. There is no way of halting as of yet. It just goes and loops through the program multiple times until it's turned off. But yeah, this code should work. So we press upload. Upload, it says right there. And this is going to take a while. Okay. It's a bit dark as well, so it looks like we're in a disco. But got no time really to do on anything else, so cue the music.
Everything is awesome. Everything is cool when you're part of a team. Everything is awesome when we're living our dream. Everything is better when we stick together. Side by side, you and I gonna win forever. Let's party forever. We're the same, I'm like you, you're like me. We're all working in harmony. Everything is awesome. Everything is cool when you're part of a team. Everything is awesome when we're living our dream. 3, 2, 1, go.
Have you heard the news? Everyone's talking. Life is good because everything's
It's about to finish. It's uploaded to RAM. Now let's start the computer. What we're going to do now is we're going to show the stepper going through the first 3 steps, and then the MDR will change because the first 3 steps of the stepper will allow the PC access to the address bus as well as the RAM, which will then output to the MDR, and then the write signal will be close to the MDR, which will make the MDR store what came out of the RAM when the PC was addressing it. Okay, so this is step 1 of the stepper, step 2 of the stepper, and step 3. Okay, those are the first 3 steps. And what that does is it allows this PC to get outputted to the RAM, which is here, and then allow the instruction to be saved into the MDR. Wait for the MDR to change on the second stepper signal. See, all zeros, because that instruction operand was all zeros. Let's just wait for the next instruction. But whilst we're doing that, these are the control signals generated by the clock and by the stepper. Each stepper has a different stage, generates different decoding signals, and these do change. Wait for them to change. See, just changed there. Okay, there we go. So they do change depending on what this stepper value is. Okay. Anyway, this should change soon. It should.
it changed. Look, there we go. So the next instruction's been loaded in, and there we go. This is the random number generator, just going away, never stops until it's outputted to the data bus where it gets accessed, but it never stops. Yeah, so anyway, a load instruction is about to come up, not a load, an add instruction. So the step is just about to go on to step number 4. So these lights have been loaded in, and there you go, and it's giving an output. These LEDs are a bit dim, but they do have power to them. It's just that they don't have a powerful enough power supply to output all those LEDs at once, but they are getting outputted to the bus. Anyway, right. These are the control signals being generated again. This switch, and it tells them which one to go to. Yeah. We're about to do a branch instruction. This is the stepper going to the branch instruction. This is the PC about to go on to the branch instruction. Branch instruction, MDR, wait for the instruction to get written into the MDR. Those are 4 LEDs, and then should get written, there you go, 4 on the program counter. Yay. I hope by executing this program I've shown that my project works, and thanks very much.